continuous time Fourier transform. You might ask yourself, we just did Fourier series, right? Fourier series is applied only for periodic signal. And just let's remind ourselves by the objectives. Why did we use from the first place Fourier series? We use Fourier series because we want to find the content of any signal, what contains from sinusoidals, so we can find the spectrum of the signal. So we can design our filter, we can design our devices. So we got to know each component, what is the magnitude or the amplitude, and what is the phase angle, what is the line spectrum. So it's important for designing filters and other applications that use signal. But what about not periodic signal? We can find the spectrum. Then they started to think about a method different than Fourier series and more general, that it can get the spectrum for any signal. It doesn't have to be periodic. So Fourier transform, it's another mathematical tool to find the spectra of a signal. And when I say spectra, it means the all sinusoidal component inside this. It's like a sum of sinusoidal. They have different amplitude and different frequencies and different phase angles. So it's another tool, but it's applicable for non-periodic. It's more general. So that can be used with non-periodic. It doesn't mean you cannot use it for the periodic. You can, of course, use it because a periodic signal will be like a special case. What is the objective? To find the spectra of a signal. Or you can say frequency analysis, to make frequency analysis. Another thing, the spectra using Fourier transform different than the spectra produced by Fourier series. If you remember when we did Fourier series, we said the sigma from k equal to 1 up to infinity, right? Then we have the DC term, the 0, the at frequency 0, but then we start from 1 up to infinity, say at frequency at k equal 1, 2, 3, 4. So when we did the spectra and we represent this x-axis by omega, then we start, you can have, of course, you have 0, this DC, and you have omega naught, you have 2 omega naught, 3 omega naught, and so on. So you analyze the spectra using Fourier series only for discrete values of frequencies. The fundamental component omega naught and multiple of it. The double, the three, and we call the second harmonic, third harmonic, fourth harmonic. That's what we got in Fourier series. But in Fourier transform, it's more general. You find the line spectra for every single value, any real value for omega. You can find omega naught, 0.1, 0.2, 0.3, 0.013. It's continuous. So in Fourier series, you get the analysis, or you get the frequency analysis for discrete values of frequency. But in Fourier transform, and Fourier transform can be applied for continuous time signal and discrete time signal, and now we are working with continuous time. So the frequency analysis, it's for all real values of frequency. That's why it's very normal when you look for the spectrum using Fourier series, you will find maybe something like that. I'm talking, of course, about magnitude. The same thing for phase spectrum, the same thing, discrete value. All right. But for omega, the frequency analysis using Fourier transform, you might find something like that. Will be like a continuous scale. Fine. So that's a big difference. Okay. All right. So we know now what the application, the difference between both. How can you get it? What's the mathematical equation used to find Fourier transform of a continuous signal? It will be, we will use uppercase letters. If you want to find the Fourier transform of a signal in time domain, we use lowercase for time domain, and we use uppercase for frequency domain. So it would be equal to the integration of this signal multiplied by E minus J omega t dt. And omega, it's from negative infinity to infinity. Observe this expression. It's not strange. When we start Fourier series, it was like sine terms, cosine term, and then we make compact term, cosine plus beta, and then we went to the exponential form, right? So this is very, very similar to the exponential complex Fourier series, except that we don't have sigma, we have integration. If you observe, if you go back and review the last lecture, previous lecture, we're using Fourier series in the form exponential complex, you'll find it's the same. Just, I mean, you have the sigma, we have the integration. So that's the way that we're going to find Fourier transform. There are conditions, and there is very important condition that this Fourier transform exists. Cannot apply to any signal. It should be applied to the signal that where the integration converge. Because if you cannot find the integration of from negative infinity to infinity for the function multiplied by exponential function, so you can find Fourier transform. So this integration has to exist. When it exists if this signal is limited, finite. How we check this? If the integration of the absolute value for this signal less than infinity. So there will be a hope when you integrate it, you get a finite value. Then you can find the Fourier transform of the signal. Maybe you can, so it's like signal like that. If you look for something like that, that's like optimistic. You can find for this one. But if you have something like that, ramp, you find that the area is just going to infinity. If it's go from minus infinity going to infinity, that would be hard. So you got to check for the that we call this existent condition. So it's okay that to have, that means that x of t, all right, can also has a finite number of discontinuities. Finite number of discontinuity. Means there are some jumps in the, if you have a signal like that, maybe, yes, there's discontinuity like that, but not everywhere. Not everywhere. And also has limited maxima and minimum. There are some point has peak value, minimum, they are limited. And you have to have the integration as infinity. These are the conditions for to find the Fourier transform. Let's take one example for something that doesn't have finite energy or finite integration. Let's look at this example. X of t defined as equal 1 for all t from negative infinity to infinity. So if you sketch this function, you will find something like that. So it's 1. And from negative infinity to infinity. Obviously, the area is just, if you integrate, you find. So obviously, it will not have Fourier transform. But let's just try, if we don't know this condition, let's try to find Fourier transform using the formula that we did. We'll say x of omega equal the integration from negative infinity to infinity, x of t e power minus j omega t dt. All right. To do that, we can say we are going to integrate it from negative t over 2 to t over 2, and then we take the limit when t goes to infinity. That's one way when you want to find the integration for some infinity for something continuous, the same shape. Take piece of it, make it from over one period, and then make this t period go to infinity. That's makes sense. And x of t is equal 1, and e minus j omega t dt. Okay. So it's equal the limit. T goes to infinity. What's the integration of 1e, or integration of e minus something? Will be the same thing, e minus j omega t divided by minus j omega. And the integration limit will be from negative t over 2 to t over 2. All right. If it bother you, t over 2, you can make it from negative t, just tell you the essence of this, from negative t to positive t. In this case, you want 2t goes to infinity, if you like to do that. It's the same thing, or from minus alpha to alpha, where 2 alpha go to infinity. It's just a way to find the integration from infinity to negative infinity to positive infinity. And you have negative t to positive t. As we said before, that's 2t. So to get rid of this negative sign, just like change the limit, right? So it'll be limit when 2t goes to infinity, and then just I will do 1 over j omega. I will just take this negative sign, and then instead of substituting by t, I solve by this value. So negative will be positive j omega t minus a minus j omega t. So that's the integration. All right. Now I start to put, if 2t go to infinity, it means t go to infinity. So 1 over j omega. Then I ask myself, e power infinity minus e power, that's negative infinity. I put t equal infinity. So I will have 1 over j omega, e power infinity is infinity, e minus infinity is equal 0. So what's the answer? Infinity. I didn't get anything. So you cannot find Fourier transform for the signal, because as you see, it's not limited. When you got the area is just extended to infinity. So that's proof that the existing condition is true, right? So we will say that yes, that's true, because if we did the integration for x of t itself that we have it here to dt, and we try it, it means you are going to integration from 1, and then substitute, you get infinity. That will give you infinity. So it means that that this does not have, it means x of t equal 1 does not have a Fourier transform in the ordinary sense. Ordinary sense means in this explanation we just did, according to the existing condition, and according to the formula that we have. But in the future, maybe in the next lecture, we will show that we can find Fourier transform for x of t equal 1, not in ordinary sense, in a generalized sense. And I'm going to explain next lecture what does it mean. So there is a general way that you can avoid some of these things. But right now, according to the ordinary sense that we explained, does not have Fourier transform in this sense. Right. Let's find Fourier transform, or in ordinary sense, for some signal, continuous time signal, that they have limited area, finite. Okay. That's example 2. Let's say that x of t is equal to e to the power of minus, let's say 10t ut. All right. Let's first sketch the signal to get sense what look like. So that's the signal. And you can substitute when you say, when first start from 0, because you have u of t. That in a step means start from 0. That's the meaning of it. So before that's equal 0, at t equal 0 will be equal 1, and then as you see is decreasing. So when t approaches infinity, the signal will approach 0, will be very small, close to 0. So that's optimistic, decreasing. Yeah. So if you apply, you'll find that the area is under the curve is limited. It's not going to infinity. So we need to find Fourier transform for this signal, and let's say continuous time Fourier transform for x of t. To do that, I'm going to apply the formula. Let me just write the formula. X of omega equal to, from negative infinity to infinity, x of t e to the power minus j omega t dt. Now, I'm going to replace x of t by the expression which is equal to e to the power minus 10t ut e minus j omega t. Then I will go, I say, okay, u of t, it means from 0 to infinity. So I'll replace the limit. Why I'm doing that? Let me explain it in more detail. Because u of t, it means start from 0 to infinity. All right. So from negative infinity to infinity, the function will be equal 0. From negative infinity to 0, it's equal 0. And then from 0 to infinity, when ut is equal 1, you have e minus 10t ut. I'm sorry, no, you don't have to write ut now because already substituted by the limit. E minus j omega t dt. So now I just have to find the integration, the second term here to the right. How you find the integration of this one? Well, you have exponential, you know from math or algebra, e power a times e power b is equal e to the a plus b. And if you have negative here in both directions, you can make it like that. So I'm going to do the same thing. So now I'll say that x of omega is equal to the integration from 0 to infinity. E, I will take negative sign, and this is my a, 10t. Even t is common. I'll take it out. 10 plus j omega and t dt. All right. So I can deal with this. I can call it a, for example. So it would be e minus at divided by minus a only, and the limit from 0 to infinity. Again, to get rid of the negative sign on the bottom there, I can say 1 over a, and then I say e to the power of 0 minus e to the power of minus infinity, right? So I get 1 over a, 1 e power 0 is equal 1 minus 0 will be 1. So it will be 1 over a. So in the end, I found out that x of omega is equal 1 over a. Now I see what's my a. That's better always just because always you'll find in Fourier transform you have just an ugly expression. So just call it one name, just one name, all right? And in the end, when you get the result 1 over a, okay, now we find what is a. It's equal to 10, 1 over. 1 over. So be 1 over, and a is equal 10 plus j omega. So that's x of omega. Let's just write it here. X of omega is equal 1 over 10 plus j omega. Oh, no. I said that's negative a. I didn't say a equal negative. You see, like this is e minus 80. So I took the negative out. I didn't call all this. I only called 10 plus j. I just called a equal 10 plus j omega. So when I substitute here, what I have integration of what? E minus 80. That's why I integrate e minus 80 over minus 8. Right. Good question. Because negative sign can make big difference. Now I have x of omega 1 over j plus j omega. What do we conclude from that? In general, Fourier transform of a time domain signal could be complex. Because as you see from this expression, it has real part and imaginary part. Great. Is the objective from Fourier transform to find the expression x of omega? If this is the end? No. It's just equation expression. But what is the value of this one? You want to know the component inside the signal. That's why the frequency component. So what? I want to see the magnitude and the phase difference changing with the frequency, omega. I want to see what's the response, what's the omega, what's the effect of omega on the magnitude of each component. So you will, originally you will substitute by values of omega and find the value of magnitude. But in general, what is the magnitude of this one? The magnitude, we call the magnitude A. A is the magnitude. That will be the absolute value of x of omega. So what's A? That's the magnitude of the spectrum. All right? So that's the magnitude of the frequency spectrum. And the phase, I will call it phi. I want to agree about some. But let's be specific. I'd like to. A is the magnitude, but as you see, A is a function of omega. And we'll see it now. Phi is the angle of the spectrum. That will be the angle of x of omega. That's the angle of x of omega. That's the magnitude of x of omega. Let's apply to this example. How you find the magnitude of x of omega? Well, you will say that A is equal to the magnitude will be 1. Is this what's the magnitude of 10 plus j omega? We got that complex number. How you find the magnitude of complex number? You square the real, square the measure, square root, right? So you'll find equal to square root of 10 square plus omega square. It's equal 1 over the square root of 100 plus omega square. And that's that you found the expression for the magnitude. Now we are going to find expression for the phase angle. Yes.
Can you remind me what J is here?
All right. How you find the magnitude for a complex number? Let me just give you this one. 3 plus j4. Can you find the magnitude of this one?
Right. It's just going to be square root of 3 square.
Yeah, because when you sketch it, you will say 3 in the top here, and you got 4. So I just direction. Okay. So that would be 5. All right. So now we'll go back. That's the magnitude. I need to find the phase. Well, I will say the angle of the top, the angle of 1, and the angle of 10 plus j omega. That's the expression. I say I want to find the angle of the top over the angle of the bottom. So how you do that? Say the angle of the top minus the angle of the bottom. That's how you do it. So let me just write this. This is the top and this is the bottom. So to find the angle, the whole thing, you find the angle of the top minus the angle of the bottom. What is angle of 1 or 3 or 4 or 5? 0. That's right. What is the angle of -5 or -6 or -7? 108. Okay, yeah, X. Okay. Minus. What is the angle of 10 plus j omega? You have real and imaginary. So if you sketch it, what do you have? You have here the real is 10 and the imaginary part omega. So that's the angle 5. So it's arctan of imaginary over the real part. Arctan omega over 10. So it'll be 10 minus 1 omega over 10. So that's the expression for the magnitude. And that's the expression for, you can say that phi is equal to minus 10 minus 1 omega over 10. So now we are preparing to find the content of a signal with different frequencies. You'll find the spectra, you'll find the amplitude, you'll find the phase. To do that, it's better to do a program and then substitute by values for omega from -50, for example, to +50, and the change 0.01, not 1, like Fourier series. Why? Because it's real. So you want to find every single thing to get smooth curve. But here in the class, I can substitute 0.01. I will spend the whole class just to take a sample. But before you take a sample, what the table look like? You put omega in 1, and then in the second row you put the amplitude, and then you put the phase. All right. So, and here you go. You prepare your table. Just sample. And can do a few, but I will tell you how you get the sense of the limit. That's important. The limit of the magnitude and the limit of the phase. When you look for this expression, 1 over, that's the magnitude, 100 plus omega squared square root. When you do that, what is the difference when you put omega negative or positive? What's the difference would make? Nothing, right? Because you are going to square it in the end. So in the magnitude here, it doesn't matter positive and negative. So if you go in the, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 1, 2, 3, 4, 5. Let's put here 0 in the middle here. The omega equals 0. Let's just find when omega equals 0. Here. What is the value? When you put omega 0 in this expression, you will have 1 over 100, square root of 100, which is 1 over 10, will be 0.1, right? So you have 0.1. Now, you are going to take the positive value of omega, the negative value of omega. You do not have to do both sides. Only one side. Let's take the positive side, and the negative side just copy, make symmetric. It's even function. And also, if you remember the spectrum, what we did in Fourier series, it was like the magnitude even function. What does it mean even function? Symmetric about the y-axis, the same thing here. All right. So now let's say that increase by 10, but you should increase by what? 0.001, because you can find. But I'm just trying to pick some numbers. But even before you do that, say, okay, what about when you go back, when you go far to infinity? When you go to infinity, what you'll get? 1 over 100 plus infinity. 100 plus infinity is equal, square root of infinity is equal, 1 over infinity is equal
0.
Great. So I know the magnitude starts from 0.1 and start to decrease to going to 0. So I expect here in the middle, you can find the values, but less than 0.1, I'm sure. because going towards zero. And since they are symmetrical with zero here when you go to negative infinity. This is a big value. Usually it's important when you are going to learn in electronics and filters, design filter, it's important to find cutoff frequency. And cutoff frequency, you just pick the one when omega equal the frequency, like what happened when omega is equal 10. When omega is equal 10, omega square will be equal 100, right? So when omega equal 10, so omega square is equal 100, and the magnitude will be equal 1 over square root of 200. It means equal 1 over 10 times square root of 2. It's equal 0.1 over square root of 2. You will learn when you take filters. That's very important when they are matching like that. So when you go for that's we did it when it's equal 10. We find equal 0.1 over 2. You can it finds equal 0.0707. And again, if you go at negative 10 frequency, you find the same thing, 0.0707. So the maximum value over square root of 2, usually they make this the cutoff frequency. It means if you have a filter. By the way, let me sketch it to you to tell you something interesting. And then you are going to say, what is the application for this one? That's the omega, and that's the x of omega magnitude. All right. And we agree that will be 1.1 here, right? And then will be like decreasing to 0. So when you look at this and you are designing, so that's a good low pass filter or high pass filter. High pass filter. Do you know what does mean pass filter? The filter allow certain frequencies to pass and then decrease the rest. You know what I mean? So this one, which frequency will pass? It has high magnitude. It becomes 0.1 at 0, means at DC. And then every time look at the frequency here, when it's low, the amplitude is high. But then when you go high frequency, it's almost getting 0. So it's getting rid of the high frequency and leaving only the low frequency. So of this represent the system, not a signal. If this represents a system, for me, it's a low pass filter. It's allow only. So if you have a signal and has many frequencies, I want just to take only the low and get rid of the high. That would be a good filter, low pass filter. Because the magnitude at 0 is high, and every time when omega is increasing, the amplitude is decreasing. So that's good. Okay. So that's one application we look at it. And that's why when I say that's when you say that when you get the maximum value, of course they can improve this filter by what? By adding gain. Like you don't want 0.1 is the gain. You want a gain equal 1. So you multiply this by 10. Multiply this by 10. It would be like 10e minus 10t is good. Why? Because make this the highest DC 1. It means no decrease. The gain is 1, whatever in, out. And every time the frequency increase, it will be decreasing. So this one is, if we say that this is the max, so we said that when omega equal 10, we found is equal A max, which is 1 divided by root 2. Usually say, okay, this is the cutoff frequency that after this frequency, when the amplitude decrease more than maximum over root 2, which is equal 0.0707, it means it will be weak signal. It will be weak signal. So they say, okay, this filter is good to take the frequency from 0 up to omega c. Omega c. That's the frequency, the component will be clear. And after that will be weak. So that's how you design. I know that it's not the topic, but I got to connect it with application, you know. So that's how they do it. And we'll expose you to also some high pass filter and band pass filter, like only if you want a certain band frequency, like you want to only pass from 3 megahertz to 10 megahertz only. You want to get rid of the rest. That's how they use them broadcasting. Well, So that's the amplitude with the frequency, as you see, continuous. So you can pick whatever you like, not as Fourier series discrete, which is good. Now let's look for the phase angle phi. The phase angle phi, that's the equation. Minus 10 minus 1 omega 10. I'm interested in discrete point, specific point. What happened when omega is equal 0? When omega equals 0, we have 10 minus 1, 0. So what is the angle, which is, it's 10 is equal 0. What angle the 10 is equal 0? Okay, we can do it, of course, in calculator, but let's say that sine 10 angle, 10 any angle equals sine angle over cosine angle. So when the 10 is equal 0, it means sine is equal 0. So when the sine is equal 0, at 0 or pi, right? So it could be theta is equal 0 or pi. So it depends on the sign. It depends on the sign. So if you have only 10 minus 1 and you put in the, to do that, what I used to do when I was students, just confusing when you put 0. I put just very small number. I said put 0.0001 over 10 and see what I get. If I get, for example, 0.0001, it means that's 0. If I got like 179, so this is 180. So that's how we can do it with the calculation. But in general, 10, 0 is equal 0 and doesn't have thing. It's 0. All right. What about if you put omega equal infinity? Omega equal infinity, when you have 10 theta equal infinity, it's, you know, it's equal sine over cosine. It means cosine 0 is equal 0. Because anything over 0 is equal infinity. So what is the angle that is cosine is equal 0? 90. Right, 90. So cosine 90 is equal 0. So I say, okay, it's infinity, but remember you got negative here. So if you say theta is equal 90, that would be equal infinity, but be minus infinity. But you have positive infinity. So it got to be negative 90. And here will be positive 90. Because phi is equal minus some. So minus, when you put infinity, omega equal infinity, time minus 1 infinity, which that will give me 90 by itself. And you put the negative in negative 90. Yes.
So based on that, the negative would the angle of 0 be then 180?
Well, that's 0. It depends. 0. What does it mean 0 first? Is 0 means nothing? 0. Does 0 mean nothing? That's a question, not signal process.
Can it also be?
No, I'm not talking about 0. Now, let's just solve. If we understand the 0, we'll understand the answer. Is 0 means nothing? No. It's something. Something. Nothing is 5. 5 is nothing. Did you study the math, the Venn diagram and the set, an empty set? Right? Empty set has nothing. Like, for example, I said the set of the monkeys living on the moon. Are you going to say 0? No, you say 5. Ah. But 0, it's a very small quantity. Very small quantity, and you call it 0. So it's a positive. 0 is like 0.00, you put 0.0000 to the end. That will be positive. That's why I make it 0. Okay. So that's now how I sketch then now the phase. Now I know it's at 0 is equal 0. At omega equal infinity is equal negative 90, and with negative infinity, omega equal negative infinity, I have positive 90 degree. So how do you sketch it? So let's just make the sketch below the magnitude. So that will be the y-axis and omega-axis. And we are going to our limit negative 90 and positive 90, right? So we'll write here negative 90, and that's positive 90, and that's omega, and that's phi of omega, the phase spectrum. And at 0, at omega equals 0, the angle is equal 0. Okay, I put 1 point here. So I got 1 point at 0. And then at omega equal infinity, to the right side, it reached negative. So you can say that's going towards here. And when negative infinity will be towards positive. So you can say, of course, you can get another couple of points to adjust how it curves. But that will be that. So you know that if you have a component, what does it mean? I want you to understand the meaning of this curve. I hate just to give you a mathematical equation, some graph, and then you know how to do it, you don't know what's the value of it. Let's just pick something at omega c. What does it mean if you pick component in this signal and this component inside the signal x of t, its frequency omega c? What's omega c? We said 10, right? 10 radian per second. So what is the magnitude? A. Found that A equal to 0.1 over square root of 2, which would say 0.0707. Okay, almost James Bond. Okay, so what about the phase? Well, we're going to substitute our equation, or you go to the graph. You go at omega c. What is omega c here? Another, yeah, you go omega c here. That's omega c. That's what, and then you go there and see the angle. Oh, this is negative, but let's check with the equation. Negative 10 minus 1 omega over 10, which is 10 over 10, negative 45 degrees. So what does it mean? It means this component at this frequency, the frequency is equal 10. 10. What does it mean at omega c equal 10 radian per second? I can find the frequency f, because f is equal to, omega is equal to 2 by f, right? So what's f? Omega over 2 pi, right? So you have 10 over 2 pi, and you get it in hertz. So I know the frequency, how many hertz. The amplitude is equal 0.0707. So I have 0.0707. And it's cosine, and the omega is 10 t, and shifted by 45 degrees. So that's the component. If I extract it, that's what it will look like. Cosine wave with amplitude 0.0707 and shifted from the 0 axis by 45 degrees. So I know how to deal with this component if I want to do any action. You know exactly what it will look like. That's the value of the spectrum. It's not just, some lines and curves. No. Every single component you want to, because maybe the shift will annoy you, so you'll try to design something to get rid of the shift. Maybe the amplitude is really low. You wanna amplify it, so it can give you ideas what you're going to do with this component that you want to extract. So these two curves, they have many things that we can get benefit out of it. Don't look at curve like, I hate when I study math, just I make curve and like that. No. You got to know how to take advantage of it. Okay, so we did that example of it. Let's just take some special case. Of course, the Fourier transform that just explained, that's the expression, the general expression that I used, that's very famous, from negative infinity to infinity, integration from negative infinity to infinity, x of t, e, and you'll be complex in general. Then they said, okay, complex, what about if I can express it in rectangular form? Because complex means there is a real part, there is an imaginary part. So I said, okay, I want to divide it into two parts. Well, let's see how we divide it into parts. So let's say now, express Fourier transform continuous time Fourier transform, I can express it in rectangular form. Well, let's see. I will start from the basic. That's x omega is equal the integration from negative infinity to infinity x of t e minus j omega t dt. Great. We know Euler identity said that e to the power of minus j theta equal what? Cosine theta minus j sine theta. Of course, if it's positive, it will be positive. That's Euler form. To express the exponential that has j, that's cosine plus j sine or minus j sine. So I'm going to use the same thing. If I look for e minus j omega t, it will be equal to what? Cosine omega t minus j sine omega t. So I will take this expression and substitute in this part. I will just take this one and replace it by its equivalent expression. So I will say x of omega equal to the integration of negative infinity to infinity x of t multiplied by cosine omega t minus j sine omega t, and all integrated with respect dt. All right. Now I will separate him into two parts. I will say then x of omega, I multiply xt by the first one. What I get? I get the integration of x of t cosine omega t minus j. I'd like to write plus j, and the other part will be minus the integration x of t sine omega t dt. So I did now two parts. Real part plus j, which is the imaginary part, right? So what about if I call this guy, I call him r of omega. So r is equal to the integration of x of t times cosine. What about this part? I will call it imaginary part, I of omega. It's equal to minus the integration negative. Let me just write it down and see if you are convinced or not. I'll call it r. The real part is equal to the integration of x of t times cosine omega t dt. That's the real part. The imaginary part, I call it I of omega equal to the integration of negative infinity to infinity x of t times sine omega t dt. Minus here. I have minus outside. So let me write this x of t nice way. So now I can write x of omega is equal the real part r of omega plus j imaginary part I of omega. So now I have the expression as in rectangular form. And then when I integrate, sometimes it's nice. I integrate multiply by cosine by sine. That's the rectangular form. And since we did rectangular form, we'll get a little bit greedy. Say, okay, polar form. What about polar form? Polar form has magnitude and exponential angle. So that's how you write it. You write a e to the power of j phi. That's the polar form. Well, but somebody will ask, what is a? Is the magnitude. The magnitude, as we said before. What is phi? Is the angle. The angle of so we can do it in this way, rectangular form or polar form. And you can apply this to the example that we did. For example, the one that we did in the example 2, what was the function? We found x of omega equal 1 over 10 plus j omega. That's what we found. You can divide it, you can express this in rectangular form. How you do that? Well, 1 I can multiply by the conjugate. I say times 1 minus j, I'm not 1, 10 minus j omega, 10 minus j omega, and divided by 10 minus j omega. So I can get rid of the complex on the bottom. Now we have 1 times 10 minus j omega at the top, and then the bottom 10 plus j omega times 10 minus j omega. Let me just do in general. If you have a plus jb multiplied by a minus jb, what you get? A squared plus b squared. And I can prove to you. What's a times a? A squared. A times minus jb minus jab. Now we go for the other one. jbe, that's plus jab. jb, j times j is negative, negative and negative positive, positive b squared. The two cancel, you have a squared plus b squared. So you multiply any complex number by its conjugate, you get the square of the first, square of the second added without using j. So saying that, when you apply, you have 10, a is equal 10, b is equal omega, you have 10 squared plus omega squared. Right? So now the x of omega, as you see, I express it as, let me write it what I got. I got 10 minus j omega divided by 100 plus omega squared. Now, if I ask you what is the real part? The real part, 10 over 100 plus omega squared plus j. You have minus omega over 10 over 100 plus omega squared. So that's your real part, and that's your imaginary part. So I think you can do it. All right. Another thing I want to say, if you know, I said, if you know the value of the Fourier transform at positive omega, you can get it at negative omega because it's symmetric, right? Let us just say this important thing. Very important property. It will help you in many problems. X, if you want to find x minus omega, what is equal to? X minus omega, it will be x omega conjugate. The conjugate of it. If you want to find the negative frequency, will give me an example. All right, the one we just did, 1 over 10 plus j omega. If I ask, find x of the negative omega, what you'll get? The conjugate would be 10 minus j omega. What does it mean conjugate? Keep the real as it is, change the sign of the imaginary part. So that'll be the conjugate. Observe that the amplitude of this one and this one, they are the same. Why? How you find the amplitude of x omega? I'll say 1 over 100 plus omega square root. And this one, 100, when you square minus omega times minus omega positive omega square. So the amplitude of x of omega is equal to the amplitude of x minus omega. What about the angle? Let's see the angle. What is the angle of omega? It's equal minus, because the one has zero angle. So the angle of the top minus the angle of the bottom. 0 minus 10 minus 1 omega over 10. What about the angle of x of minus omega? That's equal to minus, and then you have 10 minus 1 minus omega over 10. Minus omega over 10 will give it a negative. So you have negative 10 minus 1, you have another negative. Because of this negative, omega over 10 will be equal what? Positive 10 minus 1 omega of 10. So the angle of minus omega is equal to negative the angle of x omega, because it has negative, this one doesn't have negative. So say the angle of x minus omega, it's the same as angle of x, but adding negative sign. So we got two important things. How you get x minus omega and the relationship between the magnitude and the angle. So the magnitude are equal, but the angle will be the negative of each other. And how you find the expression, just get the complex. Okay. Let's just take another thing about the symmetry, about even or odd. And even or odd function, it's better to use the rectangular form. I will show you why. If you found that you have signal even or odd, go ahead to the rectangular form. It will save half the time. I will tell you why. So for the symmetry, you might have even function or odd function. And you know how you find even or odd? Odd function when x of negative t is equal x of t. Symmetric about the y-axis, something like that. That's even. Odd function when x negative t is equal negative x of t. And that will be symmetric about the origin, like that. So what's the value? If you have an even function, the imaginary part, if we're using the rectangle, will be equal 0. If you are having odd function, the real part will be equal 0. So that's number one. But how you find x of omega in this case would depend only on the real part. So it will be the integration from 0 to infinity. The real part, all right, which is equal, what's the real part? Let me just write it down. It's equal x of t times cosine omega t dt and multiply by 2. That's one even. So just have to find only one integration and easy, something multiplied by cosine. And I will go and show you an example now. What about odd? Odd, the real part is equal to 0. Right? What about the function itself? Would be equal double minus j, be imagine, minus j2, the integration from 0 to infinity, x of t sine omega t. That's the difference. So we have one integration and easy and simple. Okay. Let's have one example on the even, and we'll be done. Let's say that we have rectangular pulse. That's very important. They are going to use a lot in many applications. Rectangular pulse. We'll call it like this, P tau. It means the width is equal to tau. So let me sketch it for you, see what look like the rectangular pulse. That's x-axis, and that's the y-axis. And let's say it's like that. So let's say it's from negative 3, positive 3, and here negative 3, and the amplitude is 1. We call it rectangular pulse, and the height always equal 1. Of course, if you wanna multiply by 2, by 3, 4, then it's okay. But let's just take this one. So how we define it is 0 here and 0 here, all right? And you can write now the width is equal 6, right? So you can write it's a rectangular. It's a rectangular pulse. You write 6 like that, because this is tau. The old width we call it tau. All right. So from negative 3 up to 3, the height is equal. How you find when you look at it, is it even or odd? Even. So what you're going to do, don't go to the original one. Go to the even, which will say x of omega is equal to the integration from 0 to infinity, right? X of t cosine omega t dt. And then again, 0 to infinity, but you define only up to -3 in this example. So we'll say, okay, I'm going to integrate, I would say 2, the integration from 0 to 3, right? That's positive 3. And x of t is equal 1 cosine omega t. And then, you know, cosine omega t is equal sine omega t. Substitute. I got this expression 2 over omega sine omega 3 omega. That's what I got. Then you got it. What you observe, it's sine wave but divided by omega, and it's real. It's not complex like the first one, 1 over 10 plus j omega. So sometimes you can find x of omega real function, and if it's real function, you can sketch it. But the other one, 1 over 10 plus j omega, you cannot sketch it, but you can only sketch the amplitude and the angle. But this one you can do it. But there is something